Good morning, good afternoon, everyone, and welcome to this webinar between Xinnor and Intel. Today we will be talking about the validation that we run together with Intel in their lab on their power efficient e-course, and we will go through the presentation in a few seconds. Let's just give some more time for more people to join. Let me tell everybody that if you want to ask any question, you can do it through the chat. So the microphone is not enabled, but you can write your question on the chat box, which is on the right-hand corner of the screen, and we will answer the question at the end of the presentation. Okay, I think we are good to go. So let me introduce who I have together with me today. Myself, I'm Davide. I'm the Chief Revenue Officer at Xinnor. I have the pleasure of having Dmitrii, our CEO, and also Evgueny, who is a staff software application engineer at Intel. So why are we spending time looking at power efficiency? Power is becoming a main problem in the data center. It was already a problem in the past, and now it's becoming one of the most critical resources when planning a new data center deployment, due to the fact that AI is bringing much higher workload, and GPU tends to be very power hungry. So there are reports projecting that the power consumption of a data center are consuming as much as 10% of the global power production, which is obviously a huge number. So the system administrator, they need to think about how they can optimize power efficiency, not just on the compute side, but also on the storage side. So if we look at the storage, with the advent of high performance PCIe NVMe Generation 5, you can get 1 million IOPS from a single drive today. And actually, in about 1 year, you will be able to get 10 million plus IOPS from the Generation 6. So those drives, they are very demanding from an I/O perspective, so they create a significant amount of load on the CPU. And the I/O goes through multiple layers. They go through the NVMe driver, to the kernel, the file system, the page cache, which creates additional overhead on the CPU. So how do we cope with this problem? How do we solve this problem? From one side, we can look at adopting low power core CPU to handle high performance storage, even though originally they were not thought for this purpose. And then at the same time, try to maximize the performance per CPU. Try to build a storage solution which deliver the maximum possible performance for every CPU clock. So with this, let me hand it over to Evgueny, who will give an introduction to the Intel Xeon CPU. You are muted, Evgueny. You need to unmute.
Hello,
okay.
I'm Evgueny Khartchenko, and my role is optimization and software enabling engineer at Intel. I'm here today to give you some information on Intel Xeon Generation 6 CPUs. I guess most of you may have heard a comparison between airspace and computing industry progress made in, let's say, last 30 or 40 years. And comparison says that if similar progress would take place in aerospace industry, the cost of flight from London to New York would be less than 1p, and it would take less than 1 second. And I can assure you that Xeon Generation 6 made its own decent contribution to that progress. in some sense, this generation is special because it's the first one that introduced two types of cores: performance optimized cores, or P cores, and efficiency optimized cores, or E cores. Basically, performance optimized cores is something you get used to, I would say. So it's typical cores of all previous generations. And the E-cores appeared from client side, from Atom product line, and they are specifically optimized for the different things, efficiency first of all. So P-cores are good at single core performance. They provide decent scaling through many cores and multi-threading. They have wide and deep microarchitecture, large caches, high memory bandwidth. They operate on wider vectors and have some other accelerators. Efficiency cores optimized for performance per watt. They don't have hyper-threading, just single thread per core. And they are optimized for density, so for minimum rack space at necessary performance. And you can get more cores at the same TDP. One particular specific of this generation of E-cores is that they are focused on high integer performance, not floating point. Here is a comparison table of 3 product lines in Intel Xeon 6. So 2 of them on the left are related to P cores, and one on the right to E cores. So on the left, we have Xeon Scalable series, which is something you most likely see in your data centers. So current gen comes with up to 86 cores, is scalable from 1 to 8 sockets, and single CPU consumes up to 350 watts. It has 8 channels, typically 8 channels of DDR5 or MRD, with 6400 megatransactions per second DDR5 speed, while MRDIMMs can achieve 8000. If you look at next column, this is P-cores advanced product line, advanced performance. And here you can get up to 128 cores, 1 or 2 socket solutions, up to 500 watts, and up to 12 channels of DDR or MRDIMM, and MRDIMM can reach 8800 megatransactions per second. And by the way, Intel Xeon 6 is the only CPU at the moment on the planet that supports MRDIMMs, and that guarantees that Xeon 6 will sustain third higher bandwidth than any other CPU, just because of much faster supported memory. If you look at E-cores, you can notice that it comes up with a large amount of cores. So on widely available market, it's up to 144 cores, and custom solutions for cloud providers raise the bar up to 288 cores. It's only scalable in 1 and 2 sockets. Single CPU consumes up to 500 watts, 12 channels of DDR5 memory only, no MRDIMM support. And other characteristics like UPI, PCIe lanes, CXL is pretty much on par with P cores, because those CPUs can go into the same platform. They are interchangeable. You cannot mix P core CPU with E core CPU in single system, but single system will handle both types of those CPUs. Differences in instruction sets and acceleration. Particularly, P cores support Intel AMX, which is in-core accelerator for AI and ML, operating on short data types. And also Intel AVX 512, which is vector instruction set for 512-bit vectors. While E-cores don't support AMX and only support AVX2, which is for twice shorter vectors, 256-bit. I'd like to mention here that both of those platforms or CPUs support a bunch of integrated accelerators: Intel Quick Assist for compression and decryption, encryption, decryption. Intel dynamic load balancer for spreading network packets over cores in consistent, atomic way, and so on. Intel data streaming accelerator for copying and moving data from here to where. And also Intel in-memory analytics accelerator, which has database-like functionality and also compression decompression capabilities. You can think of those accelerators as specifically designed ASICs for particular narrow range of tasks. And this means that they are highly optimized for this task, both in terms of performance and memory consumption, power consumption. And I specifically highlighted here Intel Data Streaming Accelerator because my smart Xinnor colleagues actually make use of it in their software, which makes the solution even more efficient in terms of power and performance. Okay, from now on, I'm going to be talking on eCores, about eCores. So due to its nature, by design, they are integer optimized. They are mostly applicable in cloud scale workloads like data services, networking, media, and microservices. In typical platform, you can get up to 144 cores. And if you, let's say, consider upgrade from, most likely it's going to be something like 2nd gen Intel Xeon, you can get up to 3x high performance per watts and about 3x consolidation opportunities in terms of number of racks for particular compute capacity, which are obviously very significant numbers. This is performance comparison, and baseline in this slide is previous gen, 5th generation of Intel Xeon processors, top bin versus top bin of 6th gen eCores, 144 cores. So I'm not talking about 288 cores, it's kind of special beast. So as you can see, performance-wise, it's moderate speed up between near parity and something like 42%, maybe 1.2x speed up on average. But as soon as you can see the performance per watt, the picture is better. It's something in the range of 1.2 to 1.66x speed up, and average is somewhere in 1.4x or more, which is pretty decent because we compare just adjacent generations. And if you compare to something which could be upgrade candidate, let's say 2nd gen of Intel Xeon, numbers are just striking. So in terms of pure performance, you will see between 296 to 583x speed ups. And in terms of performance per watts, it's something roughly in the range of 2.6x, which is very significant. This is for a range of workloads that are generally suitable for Xeon eCores. Okay, that's all I had today. I leave it to you to make any conclusions, and the stage is back to Xinnor.
Okay, very good. Thank you. So let me now introduce xiRAID Opus. If you are familiar with our product technology, you are familiar mostly with xiRAID Classic, which is the version of our RAID engine operating in kernel space. But we also have a user space version of the product, which we call Opus, Optimized Performance in User Space. And that's something we introduced earlier this year. And it's meant to be used not just for local drives, but also for network attached drives. So we support NVMe over Fabric through RDMA or TCP, or you can access through vHost user BLK. We have our gRPC and CLI for the management. We support all the enterprise features and more than you would expect from an enterprise-ready RAID implementation. And it's not just a RAID implementation. It's more than that. We also have some features, which I will highlight in the next couple of slides, which are over and above the data protection that we provide with our RAID and erasure coding capabilities. This software, xiRAID Opus, operates from x86, but we can also operate from ARM architecture, likewise DPU. So if you look at the architecture, we started from the SPDK libraries that were originally ventured by Intel, and we modified those libraries to improve them. But the beauty of the implementation by working in user space is that we can access in pulled mode instead of using interrupts. And by doing that, we drastically reduce the CPU cycles and maximize the performance, as we are going to show in the next few slides. The way we use the CPU, we normally select a limited number of CPU core, and we fully dedicate them to the engine, to Opus. And the secret sauce to achieve high performance stand in the way we do vectorized calculation for the checksums. So when we operate from the x86, we use AVX2 technology, which is supported on the eCourse version. And when we operate from ARM, we use the vector register within ARM. We can deal with local attached NVMe drives, but we can also deal with network attached NVMe drives. And actually, we can also create a RAID starting from a subset of those devices from their namespaces. And we can mix and match and create different RAID groups from namespaces from different drives. We also support drive roaming, so you can move drives from a physical slot to another slot, and the engine will still recognize and assign the proper RAID group. And also in multipath mode for network attached drives, we support multipath in failover and active-active. When it comes to the connectivity, xiRAID Opus is more than a RAID engine. So we support our own implementation of NVMe over Fabric, and we support NVMe over Fabric target mode as well as initiator. So as a target mode, we can create the RAID and expose the RAID over the Fabric for drives or subsystems like namespaces. And when we operate as an NVMe over Fabric initiator, we can connect network attached drives. The protocols that we support is both RDMA and TCP, and there are many different supported configuration. So if you want to learn how to use xiRAID Opus for implementing NVMe over Fabric, we develop a step-by-step guide, which you can find on our website. The beauty of xiRAID Opus by working in pulled mode is that we can achieve even higher performance than what we can get when operating within the kernel. And this is extremely valuable when we look at random operation. So from a single CPU core, we were able to get in a RAID 6, 6 data drive and 2 for parity. We were able to get 100 gigabyte per second sequential read and 16 gigabyte per second sequential write, and 1 million IOPS random read and 0.3 million IOPS in random write. Again, this is documented in a joint validation that we did together with our partner SanDisk, and it's available on our website. xiRAID Opus is not just a RAID engine, it's more than that. We also support partitions, so you can create a RAID and partition the RAID in multiple partitions. And we also support quality of service, so you can set independent quality of service limits to each of the partition. And there are multiple limits that you can set up in the quality of service depending on mix, read, write, random or sequential workload, or purely read or purely write. So a lot of flexibility for different purposes. From a management standpoint, we develop a user-friendly CLI, which are actually based on gRPC API. So it makes extremely simple to manage the software, and you can also manage the xiRAID Opus on the local server or through a remote system as well. So the benefit of our implementation and our management tool is that we make NVMe over Fabric deployment extremely simple, and that you can develop script to integrate with our Opus implementation. So with this, now that we introduce the Intel eCores and we introduce xiRAID Opus, let's go into the details of the validation that we did in the Intel lab. So over to you, Dmitrii.
Thank you, Evgueny. Thank you, Davide. So let's discuss in a bit more details of what we actually did together with Intel. So the goal of our joint validation was to demonstrate that using Intel eCores and our software, we can gain both performance and latency, which would be fine not only for today's storage, but it would be fine as well for PCI Gen 6 storage, which will be very soon at the market. So our validation basically was devoted to compare what we can get out of Intel eCores and Intel pCores and see, do we see any significant difference for our storage implementation. I don't want to say that pCores are not fine, that's for sure fine, but our goal was to demonstrate that for our storage implementation, eCores could be beneficial solution in energy efficiency point of view, in performance point of view, and what is even more important, on latency perspective. So what we do? We as well do evaluation for different data protection schemes, because different data protection schemes matters for different workloads, especially for AI world, and we will talk about it a bit later. So let's look more precisely on our test bed. We used two same servers, one with eCores, the second with pCores. Both servers were equipped by 8 PCI Gen 5 drives from SanDisk. That drive subsystem wouldn't be bottleneck by itself. So let's look what we can get out of this test bed. First of all, look at our test approach. Our test approach, as I told, was focused on two different RAID level protection, RAID 6 and RAID 10. RAID 6 in the modern workloads, especially important in AI world when you are looking on checkpointing. This way, you need to have reliable data storage for checkpointing, for weights of the model, for the model itself, and this way you need to have very fast implementation of parity rate protection, because in this use case you have a lot of data, you have a lot of data that could be saved in a very short time window, because the main target for all such installations that your GPU wouldn't be idle. So it's about RAID 6. About RAID 10. We actually tested RAID 10 and RAID 0 because both of them could be equally relevant for inference workload. And what we already demonstrated is that our implementation of RAID 10 is fine solution for database acceleration. So related to the workload types, we used two types of workload. First, it was a 4 kilobyte random read and write workload. And basically this workload we could see in k-value cache data flow during inference of the model. Second type of workload was 128 kilobyte sequential read and write workload, which is exactly what we see during model training and checkpointing. And by the way, both workloads are fully compliant with all the standard test loads proposed by MLPerf community. So what we measured? We measured IOPS, throughput, and latency. So let's see what we can get out of the system without any RAID protection. Just if we look at the system itself and make measurements of the drive subsystem for this installation. We can see that we get 4 million IOPS without interrupt coalescing for this system. As soon as we will switch on interrupt coalescing on Intel CPU, we can get 25 million IOPS. And it's not only for Intel, the same picture we would see as well from the AMD and all the other x86 architecture. So it looks that we can fully utilize this subsystem in case if we use interrupt coalescing. The question is, what's the price for this utilization? And the price, this case, is the latency that you could see out of any requests. So you could see that this case latency will be 10 times more than in case if you don't use interrupt coalescing. So you get great performance, but you cannot get great latency in parallel. What's the problem? The problem itself is Linux kernel, this case. Therefore, our implementation of data protection in user space particularly matter to get both write performance and write latency simultaneously. If we compare what latency we can get in RAID 10 with our solution, we see that this latency is absolutely the same magnitude of order that you could see without interrupt coalescing on Linux kernel. So the question is it possible to get not only great latency, but as well great performance in user space polling mode with our product and Intel E-cores and P-cores CPU? Let's look on the numbers, but first of all, let's look what we can have as a theoretical possible results for both RAID 6 and RAID 10. Out of the 8 drive subsystem, we can get now 26 million IOPS read, which is extremely substantive number just from one server. As well, we can get out of drive subsystems more than 3 million IOPS in write, more than 100 gigabyte per second read, and 60 gigabyte per second write. Is it theoretically possible to get the same performance for different rate levels? For sure not, because data protection is as well what you pay to get the maximum performance. So for both read workloads, random and sequential, random RAID doesn't provide any penalties. So you can get maximum theoretical performance for random read and random write. Related to the sequential workloads, Sorry. Okay. Sorry, I missed by the numbers. Yeah, related to the sequential workloads. When you see at the sequential write, you see that RAID has a penalty for RAID 10. It's 2 times because you have writes on 2 drives in parallel. In RAID 6, you have a penalty related to the 2 parity drives. So out of theoretical possible 60 gigabytes per second, you can get 45 gigabytes per second. What is interesting, it's random write workloads. Related to the random write workloads, in RAID 10, you have as well penalty that you will have 2 writes per each request. In RAID 6, it's related to the read, modify, write operation for each request, and typically penalties is 3-4 times of the IOPS you can get out of the raw drives. So in our case, you can get a bit more than 1 million IOPS. So let's look at the real numbers, what we can get out of these installations. Related to the random write pattern, even if we will see at 8 CPU cores workload, which actually means that you have application which generates 8 threads of the workloads. In RAID 6 and both in RAID 10, you can get maximum theoretical performance with xiRAID, and as well as I shown before, you got a great latency. So let's see what you will get in the random read workloads. In the random read workloads, in RAID implementation, you could get in about 20 million IOPS from this server, which is more than 70% of the theoretical possible efficiency with our implementation, because for sure we have some overhead for our data paths. It's impossible not to have overhead at all when we are discussing such huge numbers. And what is equally important, then you can get in about 1 million IOPS per core from both E cores and P cores. And what is important for all the results that I demonstrated, that efficiency of the E cores and efficiency of the P cores is equal in case of using our data protection schemes. So if you look at the sequential write, you could see that you can get maximum, almost maximum performance from even 4 threads with RAID efficiency more than 80%. It means that just out of 4 threads, you can get more than 35 gigabytes per second in RAID 6. What you can see if you have just application which is using single CPU core. This case, this application couldn't generate workload which will fully utilize your server. And this case, you could see more than 13 gigabytes per second of the performance. Related to the efficiency, it's 30% of the theoretical maximum if you have maximum workload. But in this workload, you could not get more than this 13 gigabytes per second. Related to the RAID 10, you can see that you can get both theoretical maximums. And the last workload, which is as well interesting, is sequential read. In sequential read, we can demonstrate that just from 1 CPU core, we can get more than 100 gigabytes per second of the performance without sacrificing any latency at all. So it's in brief what we get in our results. Making conclusions, what is the lessons learned out of our joint validation we did with Intel? First of all, we proved that xiRAID Opus together with Intel E-cores provides very predictable latency coupled with extremely high performance, which is close to 100% theoretical RAID efficiency. What we get, it's not just our exercise. We will be more than happy then all of you as well make a trial, come to us, and we'll get the same and even better performance as well as great latency, and we will help you in all your use cases. So I think now it's right time to come to the questions. So Davide, I'm as well over to you to manage how we'll answer on the questions today.
Okay, yeah, before going there, let me remind everyone that you can look at all the results that we presented today in our joint solution brief. Yeah, you have the core code, but also Platon posted the link on the chat, so you can download it and look at it at your own pace. So moving to the Q&A, so I see there was one question from Vendel, which was related to PCIe Gen 6. So one of the reasons why we developed xiRAID Opus is indeed because we see that the kernel is becoming the bottleneck, at least for random performance, already with PCIe Gen 5. When it comes to PCIe Gen 6, it will be even more so. So we are ready for PCIe Gen 6. The ecosystem is not ready, in the sense that we still don't see any SSD being available. So we didn't have the chance to test it on PCIe Gen 6. But we believe that the problem that we can see from the kernel perspective will be even bigger. And with our user space implementation, we already have a solution that will enable to get the best performance from Gen 6. Then let me look, there are some additional questions. So a question from Hendrik, is xiRAID compatible with Linux MD? Actually, xiRAID is an alternative to Linux MD-RAID. So if you're familiar with MD-RAID, you know that MD-RAID was not designed for NVMe, so it's not designed for performance. You can get some decent sequential read performance. Other than that, if you implement MD-RAID on NVMe, you are wasting the NVMe performance. So you're not getting what you paid for. That's why we invented MD-RAID. Sorry, we invented xiRAID. So we reinvented RAID technology to cope with a new media. Okay, let me go on. Okay, following question. There is a question from Vendel about rebuild time. Okay, that's a very, very good question. So when it comes to rebuild time, we have developed a joint solution brief with our partner Solidigm. If you're familiar with Solidigm, they are the market leader. They used to be Intel, and now they're part of the SK Hynix group. They are the leader in QLC. And with QLC technology, rebuild time is one of the main problems, because those are very massive capacity drives, and it can take weeks to rebuild this drive. So if you look at that paper, you will see that we are able to rebuild a 61 terabyte drive in just 5 hours, and we're able to do it 25 times faster than MD-RAID. Okay, moving on with the additional questions. Okay, in the meantime, Vitaly is providing also more explanation. A question from Paul: are there any Intel CPU with a mix of P-core and E-cores? That's a question to Evgueny.
Yeah, those do exist, but only in client space, so not in server.
Okay.
So anything related to laptops, tablets, desktops, yes, but not servers. Probably, my guess is it's probably not particularly great option for servers, because most likely you will be looking at homogeneous software running on particular server, and utilizing different types of cores would be kind of challenge.
Okay, very good. Then a question for Dmitrii. Which erasure code do you support?
Yeah, okay. Basically, we support all erasure codes. We support all standard RAID levels. It could be RAID 5, RAID 6, all nested RAIDs. As well, we support all the parity RAIDs with up to 32 parity drives. So in one RAID group, you can have up to 64 drives. 32 of them could be for parity. And as Davide told, it could be local drives, it could be remote drives. So it could be local RAID, it could be as well, as we called it, erasure coding. So if you need more details and you is interested to test our different RAID levels, we will be more than happy. And by the way, we have some active customers who are doing our RAID 7.3, where you use 3 drives for parity. So it's not just a theoretical exercise, it's something practical. And this case, this customer used RAID 7.3 in configuration 21 plus 3 drives, as I remember properly.
Yeah, correct. Okay, I don't see any other question, but I see Vendel is typing a new question, so we might wait for him to type the question and take this last one. Here it comes. Is there an application for xiRAID for local SSD in a GPU server? Okay, that's a great question. Yeah, the answer is yes. I'm sure Dmitrii wants to elaborate more than what I do, so I'll let you elaborate, Dmitrii.
Yeah, okay. Okay, for sure, you can utilize your NVMe drives in GPU, and there are different use cases for this. It could be parity RAID, but as well, it could be even RAID 0 in case if you need to have great performance out of, say, your K-value cache. And this case, you could use in conjunction with local drives of the GPU, as well remote drives in the same RAID groups. So the beauty of our solutions that, again, you can join different drives, different namespaces out of your local GPUs, and as well remote servers, and even eBOFs. So, yes.
Okay, yeah, I think you answered the question. I don't see any more questions. So
we have one additional question. It's answer from Vitaly. Okay.
It's the answer from Vitaly. Yes, no additional question for now. So let me remind everyone that you can, whatever we discussed today, it's available on a joint solution brief co-branded with Intel, available on our website. We will also make this recording available for review from whoever was not able to join today. And last but not least, we are always open to engage in trials and POC. So if you want to test the technology, just get in touch and we will be happy to provide you a trial license and help you tune in the performance for your specific workload. Okay, with this, let me thank Evgueny for participating in this webinar and for the collaboration during all the testing. There are additional testing ongoing, so stay tuned. There might be additional news coming from as a joint validation. And let me thank everybody for being on the call, and see you in our next webinar.
Thank you.
Thank you, everybody.
Thank you. Bye.